This is AQA A-Level Chemistry. It's the Year 12 bonding topic, and this is video number 5. In this one, we're going to take on board the information from the last video about electronegativity, and we're going to start to investigate intermolecular forces. As always, I'm going to recommend that you pause as you go, try to answer the questions for yourself and complete the activities, and then you can review how you've done and see where you're doing well and where you might need to develop your ideas. So, in the first instance, these two questions might seem a little bit silly and a little bit unnecessary. But as we begin to understand what intermolecular forces are, we can use the understanding of similar words to help us to do that. So I'd like to think about these two questions. What is an international flight, and who competes in an interform competition? And in the simplest terms, an international flight is a flight between nations. A competition, an interform competition, is a competition between forms. And that key word there is between. International flight is not within a nation. An interform competition is not within a form. They are between them. So why are we talking about this? Well, it leads us to this question. What is an intermolecular force? And we've already got the answer on here actually, but let's just make it really clear. It's a force between molecules. So we've got covalent bonds here in the HCl. They are within the molecule. They are intramolecular bonds. But the forces between the molecules are the ones that we're talking about when we say intermolecular forces. Now, there are 3 specific types of intermolecular force, and the details of those are here. And you are going to need to be able to remember them, remember the order of strength, explain how they are formed. And that's what we're going to look at in the remainder of this video. So we're going to start with dipole-dipole forces. Have a read of this, have a think about it, and then review your answer. So you've been asked to draw HCl, which I've done there for you. I've done it in the upper left quadrant, and I also need to apply partial charges. Now, in the previous video, I used a tug-of-war analogy to help explain why we end up with partial charges. In this case, chlorine is the more electronegative element, so it has a greater pull on the electrons in the covalent bond, so that will end up as delta negative. The hydrogen will end up as delta positive. So I now need to draw an identical version of that just below. I've got another HCl, I've added the partial charges, and we're now thinking about where an intermolecular force would exist. Well, the intermolecular force, we need something to attract to something else, and I've got a delta negative chlorine here and a delta positive hydrogen here. So that's where the intermolecular force will form. So let's now take a look at van der Waals forces, and let's have a go at this activity. So we've been asked to draw out 2 Br2 molecules, and then we need to write on where there will be a delta positive and a delta negative. Now, based on our knowledge of electronegativity and based on what we did in the last video, there are no partial charges here because the BRs have an equal pull on the electrons in the covalent bond. But we can't then look at this and assume that that's how it ends, because that would imply that things like bromine don't have a melting point and don't have a boiling point, because there wouldn't be any intermolecular forces of attraction. So we need to look at why. So let's look at this in a different way. Now, you might need to sketch this out on paper if you want to try it for yourself, but you can see here, I have actually done what was asked. I have drawn 2 random dots on the page. I've got one here and I've got one just here. What I'm then going to do is turn them into crosses, and they now represent my electrons. Now, the question here, and you can do this looking at the screen, is based on that random positioning of electrons that are moving around rapidly and randomly within their cloud shape, do we think we would have partial charges here? What I'm hoping you can see is that this bromine will be delta negative because the electrons are closer to it. This one will be delta positive because the electrons are further away, and therefore it's slightly electron deficient. But we have to take that a step further as well. So let's take a look at temporary dipoles and induced dipoles. Have a go at this and then review your answer. So ultimately, if I've got a delta positive bromine and a delta negative bromine and another bromine molecule comes up alongside it, remember this is a temporary dipole, it's actually only existing for one instantaneous moment in time. But for that moment in time, the delta negative bromine is going to cause repulsion of electrons in this molecule, pushing them away. And that's going to create a delta positive charge on this bromine and a delta negative charge on this bromine. Now at that point, we can hopefully see why an intermolecular force will be formed. Have a think about these questions based on what we've just looked at and then review the answers. So why is there a force of attraction between the Br2 molecules? Well, let's draw those out again here. And if I've got my delta negative bromine on one molecule and delta positive on another, you can see why there would be an intermolecular force. This is not a permanent dipole interaction because this is a temporary dipole and this is an induced dipole. So this is a van der Waals force. Would you expect it to be stronger or weaker than a permanent dipole-dipole attraction? And why is that the case? Well, you would expect these to be weaker. In general, we say that van der Waals forces are around 1/10 of the strength of a dipole-dipole. And that's because we haven't got permanent dipoles and permanent forces of attraction. We've got temporary dipoles, they only exist temporarily, so the forces between a temporary dipole and an induced dipole at any one time are weaker. So what impact is that going to have on the melting points and the boiling points? Well, if the forces are weaker, we would expect the melting and boiling points to be lower. So we move on to the third and final type of intermolecular force, and that's hydrogen bonding. So sketch this out and add on all of the lone pairs and all of the partial charges. Okay, now what you can hopefully see is we've got a delta negative oxygen and a delta positive hydrogen. But the question asked for all of the partial charges to be added. So we're going to add a delta positive on this hydrogen as well. And we also need to include all lone pairs. Now, from your knowledge of covalent bond structures, oxygen has got 6 electrons in its outer shell, 2 have been used in covalent bonds, so I've got 4 more. So I've got 2 lone pairs on the oxygen. Now we're going to come back and use that again in a few minutes. But let's now think about the 3 most electronegative elements in period 3. And as you go across that period, and I have just realised the error, it's actually period 2 that we're interested in. The 3 most electronegative elements are N, O, and F. Remember that we do not have electronegativity values for the noble gases. They don't form covalent bonds, so by definition there is no electronegativity. Now that means that all of these have a very strong pull on any atom that they're bonded to. So there's a lot of information to read here. Have a read through, have a go at the activity that's in bold. And now let's take a look at the answers. So you needed to draw out your hydrogen molecules. You can see here that I've included my lone pairs. I'm now going to add my partial charges. I've put all of them on there. And what we can see is that there is a definite opportunity for attraction between a lone pair on the oxygen and the delta positive hydrogen. Now we can take this a little bit further. If we consider the hydrogen, which only has 1 electron, if that electron has been pulled by the very electronegative oxygen, it means it's almost a naked proton. It's almost totally lost its electron. And that means it's very strongly attracted to the oxygen. And more specifically, it's attracted to the lone pair on the oxygen. Let's take a look at another example. Try it for HF. So I draw out my 2HF molecules, I add all of my lone pairs and my partial charges, and we can see here again that there is a hydrogen bond between the very delta positive hydrogen and a lone pair on the very delta negative fluorine. And we'll do this again with ammonia. I can draw out my molecules, I've included my lone pairs. I'm now adding on my partial charges. And I can see there will be a hydrogen bond between the lone pair on the N and the very delta positive hydrogen. It's really important to note that hydrogen bonding is a stronger form of dipole-dipole force, but it's specifically when an H is bonded to an N, an O, or an F. So we've seen one example of each of the three of those here. Couple of questions to finish off on intermolecular forces generally. So in the first instance, we're asking why hydrocarbons that get longer have higher melting and boiling points. You first learnt about this back in GCSE when you did fractional distillation, but you spoke in terms of intermolecular forces more generally. Now we know that these are van der Waals forces. And the longer the chain, the more electrons there are. And if there are more electrons, that's a greater distortion of the electron cloud, which means the van der Waals forces will be stronger. We have a similar idea as you go down the halogens. They're all diatomic molecules: fluorine, chlorine, bromine, iodine, etc. As the molecules get larger, there are more electrons, and that means there are more van der Waals forces, stronger van der Waals forces, so the melting and boiling points increase. That takes us to the end of this video. Thank you for listening. Goodbye.